Okay, question 6. So this one is about isomorphisms. So define an isomorphism phi from a group G star to a group H sharp, where star and sharp are operations on the group G and H respectively. Okay, so what is an isomorphism? One way to say it is to say it's a bijective homomorphism. Why is that happening? Get out of here. So that's kind of a vocabulary heavy way of saying it. It just means that, first of all, I mean, if you want to get really far down, first of all, it's a function from G to H. Secondly, it respects the operation. So doing a multiplication over here in G with the star operation, and then applying phi to get you over into H, that's the same as doing phi to both of them first, and then multiplying them together in H with the H's operation. So that's what it means to be a homomorphism. But then also it's got to be a bijection, which means it's onto. So in other words, the range is all of H. All of H gets mapped onto by phi. And it's also 1-to-1. So some variation on this definition is the meaning of a isomorphism. Okay, so now prove that the image of a subgroup is a subgroup, right? So I like to picture isomorphisms like this. It's like we've got our group G and our other group H. We've got phi that goes like this. And it's an isomorphism, so everything that happens in G, the same thing's going on over there in H. So it shouldn't be too surprising that if you've got some subgroup, call it G1, well then the image of that, if you apply phi to everything in G1, and so this has got things in it like A, B, C. It's definitely got E in it since it's a subgroup, right? Well, apparently you apply phi and what you get is some subset of H over here, phi of G1, and allegedly that too is a subgroup of H, meaning it's closed and inverses and identity and everything. Now that should make sense if phi is an isomorphism, right? Isomorphisms preserve everything about a group, preserve everything about the group structure and everything. The only thing isomorphisms do is change the names of stuff. They only change the names and symbols that we're using to describe it. So the actual group structure that's there is 100% exactly the way it was, right? So it should be the case that this is still a subgroup, right? Let's prove it. So first of all, we'll start by proving that it's closed, right? So phi of G1 is closed. And I'm writing it phi of G1. Remember, that is a subgroup of H. So maybe we should call it H1. Right? Just to clarify that that's what we're talking about. We're talking about the equivalent subgroup over there in H. So it's closed. Well, let's pick two arbitrary elements of H1. And I'm gonna name it like this. And I'm calling it that because I'm gonna need to just move back over into G in a second, right? So it makes sense for me to call any two elements of H1 as phi of something and phi of something, those somethings having been in G1. And that's totally legit because everything in H1 is in fact, everything in all of H is the image of something in G because phi is onto, right? So it's totally valid to refer to elements of H this way. And then what we want to figure out is what's the product of those. And I gotta start this over. Okay, so then what's the product of these? Well, the product of these in H, so that would be this. Well, fortunately, we already know that that's the same as this in G, right? So that's to say this is a product in G1, since A and B are in G1. Maybe I should say this to be a little more clear. Right? So if phi of A and phi of B are in H1, then that means A and B were in G1. So then if we've got the product of A and B over here in G, well, in fact, that must be in G1, right? A star B is in G1 since G1 is closed, right? A and B were in G1. So phi of A star B is in H1, right? Because that's the meaning of H1, right? It's the image of everything in G1. And there you have it, right? We basically just started, we know that's the same as that. So that's in H1. So we started off by saying, you know, let these be two random elements of H1. Well, check it out, their product is also in H1. So that's what it means for H1 to be closed. Okay, how about identity? Well, G1 is a subgroup. So that means E is in G1. And it is a fact that isomorphisms map the identity to the identity. So phi of E, where that E is from G, must map to the other E, where that E is in H. So sometimes people write it like this, with little subscripts to clarify that that one's from G and the other one's from H. Maybe I'll do that. And anyway, that's pretty much it, because, because that's phi of something in G1. And so there you go, you're in phi of G1, and we've been calling that H1. Okay, and then finally, how about inverses? So, well, so again, we'll say let phi of X, I guess I'll use A, I don't know why I switched to X's. Let phi of A be in H1, so that means that was in G1. Well, then check it out. Since G1 is a group, well then A inverse, I'll use this notation now, is in G1, right? Since G1 is a group or subgroup. So then phi of A inverse, which you should know is phi of A inverse, is in, H1. Right? So these things are equivalent. That's part of being an isomorphism, right? Inverses map to inverses. And check it out. We just said, starting off with something in H1, well, then the inverse of that is also in H1. So there you go. So we have shown that H1 is closed under multiplication. It contains the identity, and it's also closed under inverses. So H1, which was just a shorthand that we were using to mean phi of G1, is a subgroup of H, right? So sure enough, since these are isomorphic, if G1 over there, if the blue subgroup over there is a subgroup, the blue subset over there is a subgroup, well then the blue subset on the right is also a subgroup. And that makes sense because these are isomorphic, so they should have everything in common except for the symbols that we're using to describe the elements. Okay.